My dear students, in the last class I have explained about diffraction, types of diffraction, difference between diffraction and interference. In today's session I am going to explain about Fraunhofer diffraction due to single slit. In order to discuss about this concept, let us consider a monochromatic source, a single slit. This slit has width E, then a convex lens and a screen. So this monochromatic light source, single slit, convex lens and the screen are arranged as shown in this figure. For this single slit AB, it has a width small e. Now in this concept we are going to find about path difference, phase difference, resultant amplitude of diffraction phenomena, resultant intensity, condition for the minima, condition for the principal maximum and condition for the secondary maxima. We have to find it. Now to discuss all these concepts, again consider a monochromatic light source W dash. From this monochromatic light source W dash, wavefronts are coming. These wavefronts are inciding on the slit of width E. Now whenever these light rays are inciding on the slit of width E, then some light rays are moving normally towards the lens and focused at point P0 on the screen. Here the point P0 is maximum intensity. Now some light rays which are inciding at the edges of the slit or obstacle, these light rays has to get diffracted from the slit and are going to incident at the point P1. Now our aim is we have to find intensity at P1, whether it is maximum intensity or minimum intensity. Now in order to get maximum intensity or minimum intensity at P1, let us draw a line AC to the line BC. Now here this is theta is the angle between diffraction angle. Now we have to find path difference between the light rays passing straight and path difference between the diffracted light rays. In order to get condition, now we have to get path difference is equal to BC is equal to AB sin theta. Now in this triangle ABC, so we have to find sin theta. Sin theta is equal to opposite side divided by hypotenuse. According to this triangle, now sin theta is equal to BC by AB. Now we need to calculate path difference between the normal rays and diffracted rays. That is, we have to find BC. BC is equal to AB sin theta. Now from this equation, AB is nothing but width of the slit. We can take this value as small e. Therefore, path difference is equal to BC is equal to E into sin theta. Now we need to get equation for the phase difference. There is a relation between the phase difference and the path difference, that is equal to 2 pi by lambda into path difference. Now substitute in the case of path difference E sin theta. Now we will get phase difference is equal to 2 pi by lambda into E sin theta. Let us say equation number 1. Now if the slit width is dividing into n equal parts, then each wave is having amplitude A. Therefore 1 by n number of equal parts into total phase difference is equal to 1 by n into the place of total phase difference, substitute this equation number 1, that is 2 pi by lambda into E sin theta. Let us take this is equal to D. Now we can take it as equation number 2. Now according to the vector addition of amplitude, now we have to find resultant amplitude of the complete wave is equal to R. That can be found by using this formula. R is equal to A into sin ND by 2 divided by sin D by 2. Let us take this is equation number 3. Now this equation number 3, in the place of D, substitute 1 by n into 2 pi by lambda into sin theta and we can discuss further. Now R is equal to A into sin n into d divided by 2. In the place of d, we are substituting 2 pi e sin theta divided by n lambda 2. So here divided by sin d by 2. Again, in the case of d, substitute 2 pi e sin theta by n lambda divided by 2. Now in this equation, this n and this n and this 2 and this 2 is going to cancel, and in the denominator 2 is going to cancel. After cancelling the respective terms, rewrite the equation. R is equal to a into sin pi e sin theta divided by lambda divided by sin pi e sin theta by n lambda. Now in this equation, let us consider pi e sin theta divided by lambda. Let us take as alpha. Now substitute fourth equation in the above equation. R is equal to a into sin of, in the case of pi e sin theta by lambda, use alpha. So this equation becomes as a sin alpha divided by sin of alpha divided by n. Now in this equation, if alpha by n is small, we can neglect a sine function. Therefore, after neglecting the sine function, we can write a resultant wave amplitude R is equal to a sin alpha divided by alpha by n. Now this n goes to the numerator, so na into sin alpha divided by alpha. Now let us take this is equation number 5. Now in this equation number 5, in the case of n into a, you can substitute capital A. The resultant wave amplitude capital R is equal to a sin alpha divided by alpha, where capital A is equal to n into small a, where small a is the amplitude of the each wave and n is the number of slits and capital A is a resultant wave amplitude. Now capital R is equal to a sin alpha divided by alpha, equation number 6. Now we know relation between the intensity and amplitude. R is equal to R square. Now in this equation, in the place of R, substitute this equation number 6. So resultant wave intensity I is equal to a divided a into sin alpha by alpha whole square, equation number 7. Now we have to get conditions for the principal maximum. What is the meaning of principal maximum? Now you can see this diagram. In this diagram, the light rays which are traveling normally towards the slit makes bright image at the point P naught. This P naught is called as maximum intensity. It is also called as principal maximum. Now principal maximum R can be found using the equation number 6. This equation number 6 can be written as R is equal to, now we are taking alpha outside, so a divided by alpha into, in the place of sin alpha, we are writing alpha minus alpha cube by 3 factorial plus alpha power 5 by 5 factorial minus alpha power 7 by 7 factor and so on. Now in this expression, take alpha outside, then R is equal to a divided by alpha into alpha. Alpha is going to cancel and we are writing only a. So a into 1 minus alpha square by 3 factorial plus alpha power 4 by 5 factorial minus alpha power 6 by 7 factorial and so on. Now in the above equation, for maximum values of alpha, the negative terms in the above equation must become vanish. Therefore, you can take alpha is equal to 0. So already from the previous discussion, alpha is equal to pi e sin theta by lambda. So now using the equation number 5 here, therefore alpha is equal to pi e sin theta divided by lambda is equal to 0. Now cross multiply here, sin theta is equal to 0 and theta becomes 0. When theta becomes 0, we can get a resultant wave intensity R is equal to capital A. Now we need equation for the intensity of the resultant wave. I is equal to square of the amplitude R square, that is equal to A square, equation number 8. Now this is equation number 8 is called as a condition for the maximum intensity at P naught. It is also called as principal maximum. Now when theta is equal to 0, maximum intensity is observed at P naught. This position is called as principal maximum. In this diagram, this P naught is called as maximum intensity. Now in this diagram, this is called as maximum intensity. This is due to the diffraction at the point P naught. Now coming to the second condition, that is we have to get condition for the minimum intensity position. This minimum intensity positions can be obtained when sin alpha is equal to 0. So in sin is equal to 0 when sin becomes plus or minus m pi. So alpha is equal to plus or minus m pi. This can be obtained by eliminating sin function on both sides. Alpha is equal to plus or minus m pi. Now equation fourth, it represents alpha value. Alpha is equal to pi e sin theta by lambda. Now substitute here pi e sin theta by lambda is equal to plus or minus m pi. On both sides pi is going to cancel. Rewrite the remaining terms. E into sin theta by lambda is equal to plus or minus m. E sin theta is equal to plus or minus m lambda, where m is equal to 1, 2, 3, 4 and so on. This is the equation number 9. This is a condition for the minimum intensity positions. These minimum intensity positions are obtained on either side of the principal maxima. Now we have to get condition for the secondary maxima. This condition can be obtained by differentiating equation 7. What is equation number 7? Intensity of the resultant wave. Therefore, by differentiating equation 7 with respect to alpha and equating to 0, that is equal to di by d alpha is equal to 0. What is di by d alpha? What is I? I is equal to resultant wave intensity A sin alpha by alpha whole square. So, d divided by d alpha into, in the case of I, substituting equation number 7, that is A sin alpha by alpha whole square is equal to 0. This equation can be simplified into, it is in the form of x square. X square differential is equal to 2 into x. Therefore, 2 into, in the place of x we have to write A sin alpha by alpha into, in the place of this x again we have to differentiate by using the method u by v whole dash. So according to the differentiation concept in intermediate, u by v whole dash formula is v u dash minus u v dash divided by v square. According to this formula, we are using here alpha into d by d alpha into sin alpha becomes cos alpha minus sin alpha into d alpha by d alpha equal to 1. So we are writing here cos alpha minus sin alpha divided by alpha square equating to 0. Now in this equation, either this term is equal to 0 or second term is equal to 0. Now let us discuss first term, that is equal to A sin alpha by alpha is equal to 0. If sin alpha is equal to 0, this value will give principal maximum. Already we discussed in the case 1. So no need to consider this equation again, because already we discussed it in the case 1, that is called as principal maximum. Now other alternate only is alpha cos alpha minus sin alpha is equal to 0. This is the only possibility. Now send sin alpha to the right hand side. This equation becomes as alpha cos alpha is equal to sin alpha. Now alpha is equal to sin alpha divided by cos alpha, that is equal to tan alpha. Let us take equation number 10. Now for this equation number 10, we have to find values of alpha. These alpha values can be found by drawing a graph. Take alpha values on the x-axis and tan alpha on the y-axis. By drawing a graph between these two variables, we will get this type of curves. If we can draw a straight line passing through the origin, the intersections of this straight line which will give the values of alpha. Now this line passing through the origin, this line intersecting at this point and at this point on the positive x-axis, and this point and this point on the negative side. So according to the intersection, so alpha values can be obtained at the places of 3 pi by 2, 5 pi by 2, 7 pi by 2 and so on the positive side, and similarly minus 3 pi by 2, minus 5 pi by 2, minus 7 pi by 2 and so on the negative side of the origin. Now we have to from this intersection alpha values are going to find. So now first intersection is observed at the point alpha is equal to 0. Now substitute alpha is equal to 0 in equation number 7. What is equation number 7? Intensity I is equal to A into sin alpha by alpha whole square. In that equation number 7, we have to substitute alpha is equal to 0. By putting alpha is equal to 0 in equation 7, we will get I naught is equal to A square. It will give principal maximum at the center of the screen. Next possibility is alpha is equal to plus or minus 3 pi by 2. By substituting in the equation number 7, I is equal to A sin alpha by alpha whole square. We are writing here in the place of I, we are writing I1 is equal to A square into sin in the place of alpha, substituting 3 pi by 2 divided by 3 pi by 2 whole square. By simplifying, we will get A square by 22. This is called as first secondary maxima. In similar way, now substitute alpha is equal to plus or minus 5 pi by 2. We can get I2 is equal to A square into sin 5 pi by 2 divided by 5 pi by 2 whole square. By simplifying this term, we will get A square by 22. It is called as secondary maxima. Now, if we can draw a graph between alpha values on the x-axis and intensity on the y-axis, this is called as principal maximum. It is called as I naught in the previous case. Then this is called as first secondary maxima, second secondary maxima, third secondary maxima, and so on. As intensity is going to decrease, as order is going to increase, this can be understood by using the graph. So this is a maximum intensity when alpha is equal to 0. That is possible when theta is equal to 0. We discussed this point at the case 1. Then alpha is equal to plus or minus 3 pi by 2, which we will call as first secondary maxima. Alpha is equal to plus or minus 5 pi by 2. It is gives second secondary maxima. So like this, as order is going to increase, the intensity of the diffraction pattern is going to decrease, and these are called as minimum intensity positions are observed at the places of lambda by A, 2 lambda by A, 3 lambda by A, and so on. This is about Fraunhofer diffraction due to single slit. In this concept, we found values for the path difference, that is 2 pi by lambda into 2 pi by lambda into E sin theta. Then second one is phase difference. Third one, resultant amplitude. Fourth one, resultant intensity at P1. Then fifth one, condition for the minima. Sixth one, condition for the principal maximum. And the last one is condition for the secondary minima. So these are the important concept for the essay question.